עכשיו אנחנו רוצים להתחיל לדבר קודם כל, רוצים לדבר על השדה, לקוונטט את השדה האלקטרומגנטי. אבל צעד לפני, אני רוצה קצת להזכיר מה זה קוהרנטיות. הנושא היום הוא, בעיקרון אנחנו רוצים לדבר על, I think I'm supposed to speak in English, as far as I recall. Okay. So, we want to talk about, our target is the quantum, הטוש הזה לא יצא לנו אחר. The quantum electromagnetic field. גם מזה לא יצא הרבה. So that's the target. But we're going to start, today will be devoted to the classical electromagnetic field, and specifically we're going to talk about classical coherence. And that has to do with our target is to understand the Henry-Brown and Twiss experiment, at least classically, and then maybe quantum mechanically, and I don't know if we'll finish that today. This is a counterintuitive target, to talk about the classical photon statistics. I don't know, it seems like if you're going to sit there, it will be a little bit, wouldn't that be in your way? Or you don't need to see anything anyway?
Nah, it's all optics.
So this sounds like, this is basically, I'm saying photon statistics, but this would be classical, or what I mean is photo detection theory for classical field. So why am I dedicating something like probably a meeting and a little bit more to those three subjects? That is because they are very fundamental and crucial in the quantum part. We're going to talk about the quantum coherence of light, and when quantum mechanically you can very easily drown in operators and then in many times people start talking nonsense. When you only learn something in the quantum language, you think it is quantum, and you actually should, knowing the classical counterpart, like what do you expect to see on a photodetector assuming the light is classical, assuming that no photons exist, just, all you hit is with an intensity of a wave. But then still, what do you expect to see on the photodetector? And the point is, why is that interesting? Because the photodetector, what do we really see? We see electrons. And electrons are discrete. So that means that at least when the light intensity is low, maybe we'll see an electron, maybe we won't. And this should be, so taking into account that the detector is discrete and quantized, but the light doesn't have to be classical, it doesn't have to be quantum. You already have statistical properties out of that. So what do you expect? What is going to be the statistics of photoelectrons? And people call this photon statistics, and that's also a bad name. Why? Because people say, and you will hear it a lot, a photon is a click on a detector. Bullshit. A click on a detector is an electron. It's a photoelectron. Whether that is a single photon remains to be seen. Sometimes maybe, sometimes not. Definitely not. So when people say photon statistics, what they actually mean is photodetector statistics or photoelectron statistics. And we would like to understand how does photoelectron statistics look when you assume the field to be classical. For example, we will see that the probability distribution of photodetection events is going to be Poissonian at best. And then when we see something that is sub-Poissonian, we can say, this cannot happen classically. So those are things that we would like to understand. And we're going to talk about the Henry Brown and Twiss experiment. Now, first of all, maybe some of you know, but still it's a nice question. How many people are Henry Brown and Twiss? Right? 2. Okay? So, Henry Brown and Twiss are only 2 people. One of them is Henry Brown and the other one is Twiss. Henry Brown was a famous and very well-known radio astronomer. He did a lot of work. Twiss appears only on one paper, which is this one. Question, where did he come from and what else did he do? The rumor is that he was actually doing some secret stuff for for some government, but I don't know. That's maybe it's a nice story. Maybe it's right. I don't know. But
You don't know
anyway, what?
You don't know what degree he had?
What?
What degree he had?
Whether he was a Dr. Twiss? No, both of them, by the way, were electrical engineers. They were not, but I'm sure, during our time when you can check it up, and then I'll know. So let me just motivate a little bit. I mean, we're going to discuss this further in a moment, but just to tell you what they were doing. And we'll also understand from that our discussion about coherence. So they wanted to measure the physical size of a star. So now, okay, for example, for the sun, we can do that. Why? Well, the sun is sufficiently close so that we can actually measure its angular width. It's about half a degree. But when you go for For example, I don't know, if I want to, and that I can do even with a bare eye.
Doctor
I
of
don't need,
Science.
what?
The answer is Doctor of Science from MIT in 1949.
Okay. But then if you look up what did he publish, now, for example, if we want to, so by bare eye we can look at the sun or the moon and we can tell how big they are. But by bare eye, that's about it. I mean, if we, I don't know, Venus or no,
Mars.
Mars. Well, those are on one hand close, but they're small. So let's talk about Jupiter. Jupiter is huge, and still we won't be able by eye to tell whether it's what size it has. But we can take a telescope, and then we'll see. What did we gain by using a telescope? What's the problem with doing this by eye? We can see Venus or Jupiter. Why can't we tell the details of it?
It's angular size.
Okay, so the problem is indeed that the angular size is small. Now, you could say, well, the problem is the resolution of my pixels, my visual pixels, my camera has, but still, but the answer is no. That wouldn't solve it. What do I mean? Even if you have a camera, a really good camera with as many megapixels as you would like, and the input lens will be about as small as our eye, with a similar focal. What is important is the numerical aperture. We're going to discuss that in a moment. Let's talk about what we call let me remind you about the diffraction limit. So you know what? Let's indeed start from that. Let's take that. This will be our motivation source. So, what Henry Brown and Twist wanted to do so the problem is this: if you have a lens with some width, and then I don't know, if you have a beam that comes, say at angle 0, it will focus here. That's the focus. This is the parallel beam. This comes from infinity. So it will have a spot, but this spot is going to have a size. It will have a width. And this width is related to diffraction. So it's about this. And D is the diameter of the lens. Now, how is that related to angular resolution? So this eventually is the limit. Even if you have the best pixels, spots are not going to be smaller than this, because this is the diffraction limit of and then if you have something that has an angular size, so let's say that you have another beam that comes at a smaller angle. Let's say that this is delta alpha, sorry. Let's call this alpha. Then this beam will also make a spot here, which of the same size, about. And what is, and if I want to say, okay, so something like, let's draw the center beam, which does not, okay. So again, so this is alpha as well. And then you can see that here there's a distance between those two. Let's call that delta x, which equals just alpha times f. The distance between, so if you have something of angular width alpha, it will cover a range which is about that. And now the question is, what is the minimum alpha that you can actually visualize? And the answer is, when these two are equal, meaning when the width of the diffraction limited spot is similar to the distance, to the angular width of the the minimal resolvable is when alpha minimum times f equals lambda f over d. So alpha minimum is just lambda over d. That means that if you want, so at least if you're using an imaging lens or mirror, of course, then the diameter of the mirror dictates and the wavelength dictates your angular resolution. Okay, and if the star is far, that means that you will need a very large telescope. Yes?
Say alpha mean you mean the minimal angle such that we can still differentiate?
Yes, that we can differentiate between the two spots, that we can tell that those are actually two spots and not just one. So what they were saying was, okay. So if I want to tell so first of all, so they had a problem. One thing is that they were doing this in radio frequency. So first of all, the wavelength is not so small, rather large. They were working, I think it was in the centimeter or several millimeter range of wavelength. In the tens of gigahertz range. So they were, so that means that if they want to tell the size, the angular size of a faraway source, they need a really big antenna. To have a really big antenna, that's annoying. You need to build a.
Cost a lot of money.
Yeah, it costs. And then they said something like, wait, all I need is so they were saying, okay, what happens if I have two small detectors, so with small antennas? So each one of them cannot, in a way, tell the size of the star. For each one of them, the diameter is way too small. So for them, the star is just a single point. But now we're going to ask. So now we're going to, in a way, reverse the process. Say something like, okay. So they were basically saying the following. Here is my star. It has a width. And here I am here with my telescopes. So now I'm going to think about just 2 points on that star. for a moment. Okay? Let's think about, I don't know, light that is emitted from this side and light that is emitted from this side. Now, those two are independent sources. So the relative phase between them is, I don't know, random, can be anything. But at any point in time, it is something. So, and given that, but the question is, what do I see here? Okay, so I'll have here I'll have here a telescope, and then maybe here another telescope. Now, okay, now let's think about light that comes from this one. So this is really, really far. So light that comes out from this one, what does it make on Earth? It makes a plane wave. Assuming this, they did that with a rather well-defined wavelength. So that you can, yeah, the star is so far that I don't need to care about the fact that these are actually spherical waves. For me, they're just plane waves. Okay, and what's the difference between the plane waves that come out from this distant part of the star and those that come out from here, from the other side? They have a slightly different angle. Okay, so there's, oops, use color. So
So the distance between the telescope is the diameter of the lens.
yes. So if I look at whatever comes from here, then this has a slightly different angle. Now, okay, and then the question is, let's assume, now if I have just one telescope sitting somewhere. This telescope sees, of course, the summation of all those wavelengths, of all those, they had two, but let's think about just one. Okay, so, I don't know, this telescope is sitting here. What does it see? Those two of them, the way they're arranged here, it seems like they are destructively interfering, maybe. Okay, I don't know. Depends on how well. So here, I see, about right now, at this phase, right now, they destructively interfere and I see low light intensity. And then, on time, these phases fluctuated independently. There's a bandwidth, and that bandwidth dictates how fast things can change. And after a while, it may be constructive and then destructive. So what we see is flickering. It acts like a speckle. A speckle pattern is the result of interference of many of sources with a random phase. At some point, maybe somewhere right now, we have constructive interference, later we'll have destructive interference, and we see a breathing. The light intensity is not constant, so it will fluctuate. Now the question is, okay, and then I'll put another, so here we see interference, and this is, and it is fluctuating or breathing.
So that's what speckle means.
Yeah, and when we say a speckle field, we mean a result of usually random interference. Like, there's not much difference between a speckle field and a double slit experiment, but in the double slit experiment, you are the source is not random, so then you can. So now I cannot tell you exactly when and where I'll see what, because this is a random object. But I do know that this thing is fluctuating. The intensity is changing over time. So now let's ask ourselves: I put here another telescope. first both of them are standing almost at the same place. Then they see the same behavior. They sit on the same speckle. So when this one breathes up and down, the other one is breathing up and down. But now I can take them, and now I can ask myself, okay, so my question is, I don't care about the intensity, I'm asking how well the intensity is correlated. So what they're saying is, okay, so now I'll move this one far away, I'll put it here. Now, from the way I drew it, it appears as if here, right now, with this configuration, those two fields are destructively interfering. But therefore here, at that time, they're about constructively interfering. So so here the correlation will disappear. So I can ask how will the intensity correlation, so the correlation factor, which is what? Intensity 1 times intensity 2 divided by average of intensity 1, average of intensity 2. What is this? Now, here they're correlated, so this is going to be larger than 1. And here they become, at some distance, they become uncorrelated. So this, as a function of distance, would look something like, I don't know, like this. And here, this will be 1. And the width of that, I don't know, let's call that xc, is related exactly to the angle. It's about the distance over which you acquire a phase of pi, or pi over 2. So if that is, this angle is alpha, and that's what I wanted to measure, then this distance is basically lambda divided by alpha, right? Lambda. So this x equals lambda divided by sine alpha, which is approximately lambda over alpha, of course. So, and that alpha is related to the size of the star. And lambda we know, so that means that basically, so we got that alpha equals lambda divided by x. The correlation distance. Sorry, I said z, so let's make it z, c, and here. So they went and said, okay, we can do that. We can go, and instead, so their trick, and well, that was a clever trick, was to say, I don't need a fancy, huge, a huge radio telescope to measure the angular width of the star. All I need are 2 small detectors, small telescopes that I can measure their intensity correlation. Each one of them will be noisy, and I'll look at the correlation as a function of distance. And so that was clever, so they published it in Nature. And then the whole physics world got crazy. Why? Because they said, well, what are you talking about? So your source is so far and so dim that you can calculate that on average you have at maximum 1 photon per integration time or something like that. So how could you even talk about intensity correlation when those 2 detectors will never click together? If what the photon can be, it's either detected here or there. How will you? All you're talking about quantum mechanically, this is nonsense. Now these 2, they were radio frequency engineers. They were damn good radio frequency engineers, and they understood waves, And they said, what do you want from us? And the other thing is that the measurement definitely worked. They did get the result. So that part, that was, so we're going to talk about this. So that's what they did. But in a way, so you know what the question was, even here, when those two are close together, the question was, if the light is so dim, how could you even ever have intensity correlations? Because if the light is so dim, then those are probably single photons. Wrong. They're not, even when the light is extremely dim. But that's a common thought. And therefore, if this one said, I have light, then this one can never say, I have light. So the question is not when you go to uncorrelated places. Maybe that was understood, that going to one. But this, the fact that they were better correlated when they're close, was something that the quantum mechanics seemed to contradict. So really, it's in a way, what are we saying here? It's like to ask yourself, what will you see? If you just take a beam of light and split it in two, and have one detector here and one detector here. And then, so this one detects. So classically we would say, I don't know, this one detects, assuming, we'll talk about the classical beam splitter in a moment, but this one detects I1, and this one detects I2 of, let's say, t plus tau, meaning a time delay between them. And then we can look at the correlation that we see. So we'll have here like correlation between the outputs of the two detectors. In a way, when they're both looking at the same time, they're both looking on the same intensity. Here there is I input of t. So if we're comparing their results at tau equals 0, we're asking what happens if, so what they're both trying to look at the same beam at the same time. Now classically it is simple. Of course, there's a wave coming in, it is split, half of it is here, half of it is here. If this one showed a click, perfect, that means there's light. And then therefore there is very high intensity probability for this one to click at the same time, because it sees the same field. So classically thinking of this as being waves, obviously, if this one clicked, it's likely that this one will click. It's even more likely that this one will click as well. And therefore, even though those detectors are clickers, we expect that this distance or this time are the same, really, because that's exactly what happens here. What do we say here? They see the same speckle. They sit on the same field. They see two copies of the same light. And therefore, if this one showed high intensity, this one will show as well. Same. And when you take them apart, it's like taking the time difference between them. Because then, this light has some correlation time, and this light has some correlation distance. As long as you are within the correlation time, you'll see better correlation. And when you get out of the correlation time, then this will disappear. And then so we want, so those two, this is a time version of the same thing. And now, so we do want to spend some time in order to understand the classical image of this, and it will be rather quick, but on the way we will also define what we mean by correlation or coherence and coherence functions, and I don't know, in a way so Henry Brown and Twist, they were saying, look, that I don't need to look at the field, I can look at the intensity. And the relation between those two was what drove. And I'll show you in a moment. This has to do with what we would call first order coherence. And this has to do with what we would call second order coherence. So those are. So we're going to spend a little bit on that, and then we are going to analyze classically the Henry Brown and Twist experiment. That will be quick, and eventually we will start to talk about, okay, so why did they knew that their light is low and that their detectors are noisy and that they are fluctuating and clicking, but still you could do what I would call how would it look? And then next week we're going to quantize the electromagnetic field, and after we do that, the week after that, we'll come back to these questions from the quantum side, and then we can say something about where everything is the same and where it is different. And the main thing that will break is the assumption that, which is very, very common, and please be ambassadors to correct the assumptions that weak light is single photons. No, it never is. So that was a little bit of motivation to where we're going, and now let's do mathematics.
Same technique to find the diameter of, say, a closer star, say the sun, or with a small angle approximation wouldn't work?
So that's actually a good question. Now, I think, okay, so optically you could do that, and I think that for nearby stars, maybe you can do something like that. The point is that in optics, it is much harder, because first, okay, the optical wavelength is much much shorter, and there's another major mechanism, and that is air. At least on Earth, you have a problem doing that because you have air turbulence. Turbulence is constantly causing, like, stars have an angular fictitious width due to the fact that the air is turbulent, and therefore, just like when you look on the road on a hot day and everything is like vibrating just from the fact that there's hot air currents. So that exists also in night. So you need to first get that out of the way, and then maybe you can do similar measurements. So I think that in optics, usually people had to eventually no, I really don't don't think that's such. I don't know for sure. When you have telescopes out in space, then turbulence is no longer a problem. And then you can do things like that, but I don't know if that is done with space telescopes. By the way, the reason Hubble was first sent up was not, I mean, it was a visible telescope. So visible telescopes we had on Earth as well. So what was the problem? Problem was turbulence. That was the main thing. So of course, what can you do outside of the Earth in space that you cannot do on Earth? One thing is that you can look at spectral ranges that do not pass through the atmosphere. But that's not what Hubble was trying to do. That's actually what James Webb is trying to do. James Webb is working on imaging in wavelengths that don't reach Earth. But Hubble at the time, so the main reason to send Hubble was to actually overcome air turbulence. So why did they stop doing that? Why don't they care about turbulence anymore? Why not make James Webb also a good optical telescope? And the answer is because we don't need that anymore, because we have solved turbulence on Earth as well. Astronomers have a way to stop the air from moving, and the way they do that is to actually just they follow. You can actively correct that. If you can measure the turbulence, then the turbulence by definition is not very fast. It's on a time scale of tens to maybe 100 hertz. So if you have, say for example, if you have a perfect source, let's say that I have a really bright star in the field. I know it's a single star. So I measure what happens to it. I measure it in real time and I see where it is moving. And then I say everybody else I correct the same way. This one is shifting all right. Okay, we shift it back to where we thought it was and shift everybody else in the same way. So if you could do that, great. Now the problem is that usually you don't want to have a very strong star in your field, because if there is a very strong star in your field, then it can be a problem. So what they do is that they make one. They want to measure the air turbulence, so they make a star, an artificial star in the sky. What do? They shoot a laser along this line of sight of the telescope. That laser goes up. It is being reflected somewhere high in the atmosphere, and then coming back down. Now, if you shoot it at the spot, this makes an artificial star at a wavelength that you choose, and then you can throw out. And using that wavelength, you can calibrate exactly this. You should be a little bit careful because you send the light back and forth, in and out. So that it acquired the turbulence twice, whereas the light that you want to look at acquired the turbulence only once. But still, that can be measured. So today they can. So today, in a sense, today they're actually doing this exactly in light. Today, yes. What do they do when they want to look at stars in the dense region in the center of the galaxy? So they take. So first of all, they image in the near IR, and then first of all they have huge telescopes, but more than one. So in Chile, in the desert, they have several IR telescopes, and like a field of several telescopes, and then they with each one they correct for turbulence, so there's no turbulence in any of them. And then they can either do an intensity correlation, but they do even better. They know exactly the phase difference from each telescope, so they add them up coherently to make like as if it's one big antenna. And with this they can see individual stars moving around the nothing, which is the black hole of the center of the galaxy.
It's a movie Netflix.
So, but now we want to talk about we want to talk about classical coherence. Now, what do I mean by the fact that I say that I have a coherent, that my light is coherent? So I want to explain that what is coherent light and what is incoherent light. Coherence is knowledge. Coherence, it has something to, it doesn't tell me much about the light source. It tells me something about me, about the relation between myself and the light source. What do I know about it or don't? So it's just, I would say that coherence equals knowledge. In a way, coherence is very much related to entropy. You know, in this gas, there are many atoms, they're moving at different speeds. And at least conceptually and classically, if I could know where each one of them is, I will be able to tell exactly where they're going. And I'll be able to tell their history and their path and their future deterministically and completely. The problem is that I don't. And let me compare the question, what is what I would call coherent light and incoherent light? Let's think about what happens in a pool. So if this is a common Israeli swimming pool with common Israeli kids in hot summer, so there's many of them in the pool. They're going out and jumping in, and they're generating waves in the pool. But those waves are, you have each one of them is a source. Let's say even a point source, but they turn on and off randomly. And if I ask myself, okay, so what are the waves in the pool? I don't know. I can talk about averages. Maybe there's an average intensity. Maybe there's what's the average distance between kids. What's the all kinds of averages that I can ask. But I don't know. But let's think of I don't know. We'll take German kids. They're much easier to handle. And then we'll take them all, tell them, okay, you stand on the pool edge. And now, hold hands please. And now, 1, 2, 3, all of you jump together inside the pool. Then what you'll have in the pool is basically a plane wave that is generated. Or basically if my sources are correlated, I have many sources that are emitting together, and they will generate a nice plane wave. So the difference in this case is knowledge. In one case, I didn't know when each source was going, and in the other case, I knew. What did I know? I knew relation between them. I didn't care exactly when a specific kid jumps. Because but if all of them jump together, then I know that what I'm generating is a pulse that is really a plane wave that is going to propagate in the pool. It will hit the other wall and then something. What I just told you is the question of, I want to say something like, okay, the main thing has to do with something that I just said briefly. I don't care exactly when each one jumps. Okay, maybe I do care. And with kids jumping, I can ask this question. But with light, I cannot. Because the exact time is phase. And I cannot measure phase. So I don't know if I can say, look, the question is, coherence is knowledge. And knowledge of what? Say of the intensity of the field. Now, but what do I just now I cannot know this. But what I'm asking you is, assuming I did, will that allow me to predict the field somewhere else? The answer is, if they're correlated, then yes. Okay? So if there is coherence, there will be, if 2 points are coherent, then the field at position R1 and the field at position R2, like that, and on average, they will be correlated. So I can say the same in time. This is the correlation of the field. Of course, I can ask, generally those are points in space-time. But when we usually ask, okay, what is assuming I'm looking at this same beam, same location, different times, or same time, different locations. But of course, you can ask, generally, this is the question of how is the field of R1 and T1 related to the field at R2 and T2. If you want, those are even generally. Now this is a classical coherence. Sometimes people mark it with G or gamma. And this is the function. Now what is this? This is a function of T1 and T2. And this is G1. Why 1? Because in a moment we'll talk about higher orders. So this is, and if the light is stationary, meaning that if there's no T1 and T2 are not special, if the light is stationary or ergodic and all of those things that you already heard many times and never understood exactly their definition, and that is that this is basically like G1 of tau, which is the time difference. Tau equals T1 minus T2. And this one is indeed, it's the same G1, but this is of R1 and R2, and it will be let's call it rho. And this is so and generally we can talk about so this will be and how do we, and if I want to normalize this, what will I normalize it by? And I will say what?
Rho means the mean.
Means of what? That's the point. It has to be the mean intensity, not the mean of the field. Because the mean of the field is usually something that I don't know. It would be 0. So let's see. Okay, what do I normalize this by? I will normalize it by the case that I definitely know. What do I know? When T1 equals T2, then you know that you have perfect correlation. So the normalization, and then usually people write something like G1, G small 1, which is the normalized one, is what? E of T, E star of T plus tau. Now, and then there's this average, and we're going to talk about the average in a moment, divided by this. And I don't care if I write here E of T or E of T plus tau, because I assume that the light is stationary. But it doesn't, the average is the same. Now, average over what? This is the average over the, let's call it ensemble of possibilities. That's what I really want to say. Because I have an instance. At a specific point, like if I take an image of the pool at a given point, I know exactly where each kid is. I know, and I assume that I know how they're moving. Let's say that what all they're doing is like this all the time. Okay, each kid, that's all that they're doing. So I know where each one is. I know exactly the relative phase right now. I'll know everything. But of course, I'll take another snapshot 2 minutes later and the kids are somewhere else. So we're talking about the ensemble of possibilities for the source to be arranged. In many cases, it can be also an average over time. When, if the light is stationary and ergodic, then we can assume that over a long time, then an average over the ensemble is equal to an average over time that delivers the average over the ensemble. Now, we're going to look into G1, more deeply in a moment, and explain how can we measure it. How can one measure G1? I'll show you. It's easy to do. But because we already wrote that, let's say immediately what would G2 be? Okay? So let's see. G2 is what Hunbury, Brown, and Twist were measuring. Now, okay, so here, let's be careful. What did they measure? They measured the following. They just looked at the intensity. They were looking at, they were measuring G2, and don't copy yet. They were looking at this. They average the intensity at T1 times the intensity of T2 divided by basically the average intensity of T squared. What?
Oh, no.
What R?
Instead of time.
So when they...
What do you mean?
They measured in relation to distance.
Yes, but this would be a time version of Hunbury, Brown, and Twist experiment. Of course, now I can look at this and say, look, what is this? This is E of T, E star of T, times E of T plus tau, times E star of T plus tau. And that's why, okay, so this, there are in here, the field does, so this one is G1, because the field appears once, and the conjugate appears once. In this case, this is G2 because the field appears twice, and the conjugate appears twice. But this is a specific kind of G2. You could have many others. So this is at the same parameters. I could also say, so G2, there's actually a family of people. Many people would say, I measure G2. What they mean is the intensity correlation. But let me show you another G2. This is G2 intensity.
But it's a lowercase g because it's normalized, no?
Yeah, this one is normalized, right?
So it's a lowercase g.
Yeah, this one is the lowercase.
Oh.
But I'll stay with the. So this was G2 for the intensity. Let me show you G2 of a field, E squared. That's something else. This is, okay, let's do this. E of t squared, E star of t squared. That's also, sorry, that would be t plus tau. Let's just write it. That's a different case. This was the correlation of intensity between different times. This is the correlation of the field squared in different times. Of course, generally, I could have more than one delay. I could have here so basically there could be 4 times here, and then that means that this would be a function of 3 the most general this is still a function of only 1 tau. This is again also a function of just 1 time delay. In general, there could be several things, and that is, here we will have, I don't know, E of t plus tau 1, E star of t plus tau 2, E star of t plus tau 3. I don't know. So basically there are tau 1, tau 2, tau 3. 3 possible. I can choose. Now, admittedly, of course you can identify that this is a family of those, but it's not so clear when will you be interested in something like that. But there are cases, clear cases, where you're looking at the correlation of intensity and also in correlation of the square of the field. I'll show you fields. I can talk to you about fields where the field is incoherent in G1, incoherent in G1, but shows perfect coherence in E2. So in the square of the field. I'll tell you when that can happen. If you have a field, the field is complex. But let's say that it is complex, but it is real. Okay? So it's either pure real or pure imaginary. And that means that if I look at the field as a function of time, it's real, but it's random. So it can be anything, I don't know, plus, minus. So on average, that's 0, and it is fluctuating very fast. So if I look at the correlation between that field, which is random and real, between now and the slight time, very quickly, there is no correlation. Because it is changing very fast. But as I told you, it is real. Therefore, if I square it, it's always positive. And therefore, the correlation of E squared as a function of delay can conceptually be infinite. So this would be a field that has a very short coherence time in the field, but an extremely long, potentially infinite correlation time in E squared. The same can go for, and of course, this also, as we said, can show correlation. I'll give you another example. This is the intensity. The question is, if I know the intensity 1, now will I know the intensity later? It doesn't say anything about the phase, doesn't care about the phase. So to say, do I know the field? I need to say I know the phase. Why? Because you see here, this contains a phase difference between T1 and T2. What I ask here, and in a moment we'll actually do this, we'll understand that what we're asking is, the major question that we're asking is the phase stable? Meaning that if I know the phase now, will I know it sometime later? Or if I know the phase here, do I know it also there? If it's a perfect plane wave, yes. If it's a perfect plane wave, I know the phase here. Yeah, I know it's a plane wave, so I moved here. I know exactly how much phase I need to correct because this is a deterministic phase. So this asks about the stability of phase in space, and this one asks about the stability of phase in time. Now, but this one doesn't ask anything about phase. It only asks about intensity. So a field can be, what is coherence G2 in intensity? Constant intensity. If the intensity is fixed, perfect. This will show perfect correlation. Or, I don't know, it would not depend on tau. At any tau, it will have something. And if the intensity is random, then it will have some correlation time. So that, right now there's a fluctuation, so the intensity is higher. For some time it's going to be higher, and then it will no longer be higher, and I don't know. And this will be on the average after the correlation time of the intensity. Or space, same thing. So we defined those, we talked about them classically. We understood that, I told you something like, okay, so I want to, and now I want to dive a little bit more into G1 and to tell you, okay, so how do we measure it? That's very simple to measure. But maybe now, after an hour and 15 minutes, is a good time to take a break. So we'll talk soon about G1, how it's measured, and what is the classical beam splitter, which has to do with that. And then we'll, So let's say something first about how coherence is measured. And and the general answer about this is, let's think about how we would measure the first order coherence, and then we'll see how to discuss what we're going to measure in other words. So if I ask myself, so let's see how to measure G1. So G1 is this, E of t, E star of t plus tau. So what I can do is, okay, so I want to look at the multiplication of E at t and E of t plus tau, at t and tau. So let's do that. Let's take a field. Let's split the field. Okay. So here here E comes. And then, so I'll explain, and then we'll discuss, let's say, a little bit more about the beam splitter. So the idea is, let's say that here I split the field. So here at some time E of t arrives over 1 over square root of 2, but let's forget about that one. And then the other part go through a delay line, which is longer. And therefore here what comes is the same field. And then what we do, how do I, so let me show you how we can measure their, so what I would like to measure now is their multiplication. So we meet them again on a beam splitter. And in a moment we'll discuss the beam splitter slightly better, slightly in more details. But let's think of this as being a 50-50 beam splitter, and therefore what I have here is the sum well, let's have this 1 over square root of 2. Then another one square root of 2, so I have here half this. And here, just due to, here it has to be minus. And now, I'll put here a detector, and here a detector, and I'll take their difference. Why? Well, because here I have the intensity. So I have this, E of t plus, sorry, in this case it's going to be minus. Absolute value squared. And here, well, huh? Can. And here, of course, I'll have and now, okay, so you can see, well, what is this? This is, well, there will be a quarter here times what? Times the intensity at t plus the intensity at t plus tau plus twice the real part of E of t E star of t plus tau. Why? Well, because what we actually have is E of t E star of t plus tau plus E star of t E of t plus tau. Do you agree? And the same will be here. So that's what, so if this is I1 and then I2 equals basically a quarter intensity of t plus intensity of t plus tau, and the only thing is that minus twice the real part of the same thing, and therefore the intensity difference between these two, so I1 minus I2 is just simply that. So it's actually a quarter of 4 times the real part. So it is what? It's the real part of E of t E star of t plus tau. So it measures the real part of the and now if I take an average on this, I'll take an average on this. So an interferometer, an unbalanced interferometer, measures the coherence function. Now, see. So, and now the point is that the question, boom. אין לזה מגנט, שיש לו מגנט. So, now this is measuring the temporal coherence. Now what will we see when we do that? Well, okay. Let's assume that this field is a perfect cosine. Okay? So okay, let's say so if E of t equals, say, amplitude e to the I omega 0 t. So that is a perfect ideal monochromatic field. Ideal single frequency. Then, well, then that means that E star of t plus tau is simply a e to the minus I omega 0 t plus tau, and therefore E of t E star of t plus tau is just simply e to the I omega tau, or minus, I don't care, and it's this a squared. And then, so, and if I, and that is all, that's all there is. And so if I average this, it doesn't matter. There's nothing to average. It's always this. And therefore, what will I see here? Well, I'll see the real part, so that indeed I1 minus I2 in this case will just be cosine as a function of tau. Will just simply be cosine omega 0 tau. Let's assume that it's normalized. Okay, so the normalization takes away. So that means that the correlation function, and okay. And then what happens if the frequency is not so well defined? Okay, so there is an uncertainty of frequency. So if, we'll see that in a moment more mathematically, but so this is like, so that means that this is just simply, this is a cosine function going on forever. Now let's assume, so if the field has I don't know, like some amplitude, maybe the amplitude has some time dependent, and then here it will have some e to the I omega naught t plus some phase that may depend on time. So now everything remains almost the same. So, and that is, so this would be like a narrow band. I can say this in two ways. In a moment you'll understand that if I talk about phase or I talk about frequency, it's about the same thing. Why? Because the frequency is just the derivative of the phase according to time. So I can think about frequency saying, look, you know, that it's a narrow band, but it's not perfectly single frequency. So I don't know exactly the frequency. Maybe it's omega naught plus small delta. Maybe it's omega naught minus delta. Or like I can say that omega 0 can be plus or minus delta omega. There's a width to that. Now then, what will happen to the coherence function in this case? Well, it will oscillate according to the frequency, but I don't know what the frequency is. So if this is omega 0, at omega 0, it would look like that. Sorry. And at omega 0 plus delta omega, it will be slightly faster. So initially they would look about the same, but then slowly they will grow out of phase, and eventually it will. So this is for omega 0 plus delta omega. So now, since I don't know, I need to average over all those possibilities. And then, so they start in phase, and then at some place they go out of phase. Where? Basically where the frequency difference, the unknown, the frequency uncertainty becomes times tau becomes of order pi.
You get the beating, no?
Yeah, I mean, it's not a beating because it's a question of, now it's a question of knowledge. I get either the black or the red. I just don't know. The frequency is unknown. There's a frequency uncertainty around this. So that means that I will get this, but it will be multiplied by some envelope. So what will I get then? In this case, I'll get something that looks like, it will start like this, but it will eventually decay. Why? And this envelope will have a width of tau correlation, which is or delta omega, sorry, about approximately pi divided by delta omega. So I can show this to you directly. Okay.
Why would it decay?
What?
Why would it decay?
It would decay because here sometimes I see constructive, sometimes I see destructive, or sometimes I see positive. On average, I see nothing. Here I see the cosine. It really doesn't matter because the phase difference between cosine omega tau and when tau is small, all cosines are 1. Meaning any field interferes with itself at delay 0 because it's the same field. It will be all interferometers at delay equals 0 will show constructive, perfect constructive interference. But when you start introducing delay, then now the question, will I see constructive or destructive, depends on the frequency. And if I don't know the frequency, then I'll see a random result. Sometimes I'll see minus, sometimes I'll see plus. On average, I'll see 0.
How do you define tau c? Is it when the intensity goes to a half initial?
Now, look, this is measuring the intensity difference, right? So if we think about that, what happens when you have perfect coherence? The intensity fluctuates between everything here and everything there. And that's why you see this cosine omega 0t. And then what? Okay, so when you start introducing small delays, then you see interference. Complete constructive here, then back here, and so on. And then, at some point, this contrast dies. Why? Because then you don't know. I mean, sometimes it is constructive here, sometimes it's constructive here, but I don't know. It becomes being random. Now we can make this a little bit more mathematical to show, or I can look here saying if the phase is random, then I could even write exactly what we just wrote, that the average of E of t and E star of t plus tau equals what? It will equal, well, it will be here, a squared. Let's assume that the intensity doesn't depend on time. Okay, let's assume that all the noise, you know what, this is, well, never mind. Let's call it, let's leave it like that. So I'll write here a of t plus tau times what? Times e to the I omega naught tau, same thing, times e to the I delta phi of tau. Or let's write it e to the I phi of t minus phi of t plus tau. And now we're going to average over this. Now the average of this is intensity. So unless there's some crazy, let's assume that there's no pure relation between the intensity and the phase. So I can say that, look, this on average, I want to look at the e to the I omega tau. This is completely deterministic, so this can just go out. But I'll average this, and I'll say I need to average this. Now the average intensity, well, it's a number, and if you assume stationarity, this is basically going to be the average. This is of the order of the average a squared. I don't know. But here, so there's e to the I. But here, there is, we're averaging over phases. So at tau equals 0, this is perfectly 0, so this is constantly 1. But when tau is larger, then the question is, how is the phase still the same? Or did the phase change? And when the phase can acquire a difference of pi, then everything is out, because you can have constructive everything. So if this can be both positive 1 and negative 1, then you're out. And what is this? The phase difference is, as we said, just the frequency difference times tau. So I ask myself, when is this pi? At tau c, at the correlation time, it will be pi. So that's why I told you, look, also looking at it from the phase kind of way, we can see that when we acquire it, when the unknown frequency, the frequency difference can bring us a phase of pi, then we're out. Now let's see that in the most direct way. And mathematically we can also do that, because we remember, so let's see, what is this? Well, assuming that the light is stationary, I can say that this is 1 over integration time, integral from, I don't know, minus t over 2 to large t over 2. So I'll integrate over time, a large time. And I can even say that it is this at the limit of t goes to infinity, so large time. What? Just this. This is assuming stationarity for stationary light.
What does it mean?
What I'm telling you is, look, I'm going to average. I just told you that if you measure the intensity difference, you'll get the real part of the coherence function. If you measure the intensity difference of an interferometer that I just erased, then what you're measuring is the coherence function. Well, not exactly. You're measuring the multiplication. Now then, there comes a point. Do I measure in the instantaneous intensity difference? No. I always have, my detector has an integration time. Right? So, and this integration time is not so short. Definitely not instantaneous in terms of the field. The field oscillates up and down at an optical frequency of hundreds of terahertz, and I integrate the fastest I can is, I don't know, a nanosecond, 100 picosecond. That's what my detector is. So a detector always integrates over time. It can be a very short time, or you can integrate for a longer time. If you look at if this light is very dim, or if you have any other reason, you can integrate for a day if you want. Okay? So, and now, so every detector does this. Every detector always does this. And every detector does not give you, when we say I of t in a detector, we do not mean this. What we actually mean is this. What? I have a window, and I look on the average intensity on that window. Now, what did we measure over there? We actually looked, what did we have here before I wrote that? I remind you the drawing. So I had here an interferometer, where I had two detectors. Initially I told you, look, this measures I1. Now I tell you, no, you don't measure I1. What you actually measure, and I1 was what? E of t absolute value squared plus E of t plus tau absolute value squared plus the real part of of E of t, E star of t plus tau. I guess you remember that. Now I told you this. Now I tell you, no. So that would be the intensity of time t. Now I just tell you, you don't. You measure the average of this over the integration time of the detector. Okay? So if I measure this over so that means that by definition, I'll be measuring, I'll measure the average of this and the average of that. That's okay, this will be, this detector will measure this as well, and this part will go away. But I'll be left with what? With this. But not instantaneous value, but average value over the integration time of the detector. Now, and as I told you, this integration time of the detector is always many optical cycles, because the optical cycle is about 3 femtoseconds, and the integration time at minimum is 100 picoseconds. So those are, so I'm doing this over a long time, and if I want, I can even make it longer. So we always measure an average over time, and we can decide it will always have some minimum length, and it can always be longer. And I tell you now that let's look at the fact that, okay, so this is what any detector does. And this is the let's call it, I don't know, let's call it T detector. And now, so, and we are generally looking at the case where this time is large. So let's assume that what we're doing is something that is similar to that. So this is what we measure. Now, but if this is, we measure the right side, but if the light is ergodic, then we actually got the left side. So this is what we measure. Now, but this, what is written here, that's a convolution. I forgot the stop. So this is so that's the correlation of E with itself. So if I do a Fourier transform, so this is G1 of tau. So what is the Fourier transform of a correlation?
Spectral density.
Yes. So that means that G1 tilde of omega, Fourier transform between those two, is just that is a correlation in time is a multiplication in frequency, but this is an autocorrelation. So therefore, this is a multiplication of. So this is E of omega multiplied by E star of omega. So this is this absolute value squared. Now this is important. So if I measure, so that means that if I measure this in time, so if I measure G1 in time, Fourier transform, and I don't know the field, I don't know the phase, the spectral phase, but I know the intensity. I know the spectrum of the field. And therefore, what I wrote here, what did I write? Where was it? Here. You saw like tau C equals pi over delta omega, or the fact that delta omega times tau C equals pi. This is actually the Fourier relation of time and frequency. That means that if, I don't know, if this has omega 0, so that if that is E of omega absolute value squared, and it has, I don't know, it looks like that, and it has a width of delta omega, then I know what the correlation time is, because, okay, just Fourier transform this intensity, which can be measured, and then you will know. So that means from this I immediately know that the correlation time is just pi or 2 pi divided by delta omega. Okay, so and so I actually now even told you how do we measure the spectrum of a laser? I'm really asking. Huh?
You can measure when its correlation case down to some zero. when
Yes,
it's
that's actually the less intuitive way. And of course here, and that's actually what you do when you have something that is really narrow. I mean, normally what I'll do is I'll take a spectrometer. And the spectrometer, what do? We open the spectrum, we open the different frequencies, and we measure. We actually open them in space. We use a grating or a prism to spectrally separate the light, and then what? I don't know, scan it with a single detector and find out how it looks. But then you have a spectral resolution. The spectral resolution has to do with your ability to separate different frequencies and to actually, and if you remember, it's related to the angular uncertainty before, because every frequency will have a different angle. The two close by frequencies will be hard to tell between, because the two spots will be almost overlapping. So diffraction limits also this. In any way, a spectrometer has a finite resolution. And if the laser is sufficiently narrow, I won't be able to tell. I don't know, it's sub-resolution, I don't know. So I have a really good spectrometer with a resolution of 0.1 nanometer. 0.1 nanometer is still quite, it's very small compared to 500 nanometers, but still not zero. Things can be extremely narrower than this. So if I have a really good laser that is narrow band, I put it on any spectrometer that I have in the lab, I see a perfect single pixel. So if I want to measure that, then this is what I'll do. Because this becomes easy. Because then the tau, the integration time, the delay, the relative delay to measure will be long. And to make long delays is not hard. So you just take, I don't know, take a fiber or okay, so that, and this, and the fact that the relation between and really the main thing is the fact that, if you have all those frequencies in your source, then that means that if you introduce a delay, you don't know how much phase you added. If it's a single frequency, you know exactly how much phase you added. But if you have a bandwidth, then you don't know. You have an uncertainty of phases. And therefore, this thing dies. Now let me say something about non-stationary cases. So far I assumed a stationary light, meaning I assumed that there's no dependence on time. But let's think about a different case. If I have a bandwidth, this can be a pulse, a short pulse, transform limited pulse. And then, but still, so the question is, does this hold for the case of a stationary light? And the answer is non-stationary light. And the answer is actually yes. What do I mean? but it means it holds in a different way. Okay. So if what comes here is a pulse, then I split the pulse and then meet it again. Now, if the delay is small, then the pulse meets itself at the same. So if what I have here is I don't know, a pulse, then here I will have, I'll see, and so this pulse is being split twice, and then it comes here to the detector, and then so we have a field, and it's time delayed picture. This is intensity envelope, this time is the delay tau. Now, it's the same pulse, so within the overlap region there will be interference, but the overlap region is slowly going down. Eventually you will come to the point where those two pulses don't overlap at all, and the interference between two non-overlapping pulses is zero. So this contribution of the, when I take the difference between these two, okay, initially this one will maybe see constructive interference in the center, and the other one will be destructive interference in the center. So the intensities will be different. But as the delay becomes comparable to the duration of the pulse, or larger, then the interference effect dies out. All you see, this physically disappears. It doesn't exist. Because E of t times E star of t plus tau is zero. Tau is too long. It's beyond the duration of the pulse. And then both of them detect only this. This thing is just, it's not that it averaged to zero. It is physically zero. And then, okay, so this detector detects this one detects the same. The difference is zero. So even if you have pulses, it's exactly the same thing. What this tells you is that there is a difference between time delay and phase. Okay, the phase assumes that you know the frequency. If you have frequency bandwidth, then there is a difference between a time delay and a phase. Okay. So having understood that, we can actually understand what we need to do in order to measure higher orders of coherence. Now, let's suppose that I want to measure the coherence of E squared. Well, then I need to, we'll need to, I think, I'll delay that. We need something that squares the field before we do that. I would like but for the case of the intensity, that's even easier. You don't even need the interferometer, right? All you do is you split and you put two detectors. Detectors, they give you intensities. And then you can tune the delay between the detectors as in any way you would like. That's why G2 is so common, because it is so easy to measure. Okay. So now we have something like 15 minutes. Okay, I'll say something quick about the general properties of the beam splitter, and then we'll start to say something about classical photon statistics. should remember that this is non-magnetic. I tend to forget. So the general beam splitter has two inputs and it has two outputs. Now it has a reflectivity and a transmission. And usually we can say something like, and it makes sense, look, E3 is the transmission of E1 plus the reflectivity of E2. It makes sense. But the point is, and then E4 equals what? And then you could say, looking at this, you could say something like, look, this is the transmission of E2 plus the reflectivity of E1. But if we write it like that, and we assume that T and R are real positive numbers, we run into an immediate contradiction. Because this does not preserve energy. What do I mean? Energy coming in is E1 absolute value squared plus E2 absolute value squared. That's the energy, or this is actually the power. This is the total power in. And at the output, well, we'll have and you can check by yourself very quickly that this is not equal. For the simplest case of this being 1 over square root of 2 and this being 1 over square root of 2, then clearly here you will have
the mixed value, the RT E1 E2 twice.
What?
Mm-hmm. Just from each one of them, the TR E1 E2, the mixed
right.
The mixed value.
Yes. And so first of all, so that means that we have a problem. There's and so what do we need in order to preserve, to have, and this needs to be, if this is a passive beam splitter, then the total energy in must be total energy out. So how? Now, and the answer is, there must be and honestly, we should remember that maybe the transmission is, like, okay, so the beam splitter has two sides, right? And the reflection here is from this side of the beam splitter, whereas the reflection here is on the other side of the beam splitter. They don't have to be the same. Definitely they don't have to have the same phase. Actually, they must have an opposite phase. So we need to, so let's do that. So let's say that in the most general way, I can say that E3 and E4 as a vector are related to E1 and E2 by the beam splitter matrix. What is it? It's, I don't know, E3 and E1. This is T, 3, 1. And this is R.
3, 1.
What? R4, what?
3, 1.
I think so. And this is R2, 3, and this is T1, T2, 4. Am I right? I think so. I don't remember. Something is that's probably wrong. R14. Yeah. Yes. So the question is, what is the relation between these guys? And then we can say, okay, what I need is I want that the total length of this vector, being the E3 squared plus E equals this square, and we can make requirements out of this.
The beam splitting matrix must be 1, no?
Right. So one thing. So first, what you immediately see is that the intensity of a beam splitter must preserve energy being. So the requirements of energy preserving are two. One is that T31 equals T24 absolute value, and it equals some kind of something that we can call T, an absolute value of R14 and absolute value or R32. They also must be some equal, and T squared plus R squared equals 1. This is one thing, but there's another thing, and that is that there must be that there also a sign between. We can calculate that, but we don't have time, and I don't want to waste too much on this. So that's one requirement. That's requirement 1. And the requirement number 2, I'll just give you 2 examples. There's a total phase. Let's say something like this. These coefficients can be complex. When you go through a beam splitter, it has a width. If you have a width, it will add a phase. So the transmission has a phase. The reflection has a phase. So those are generally, but what must be is that there should be some relation between them, and I'll give you 2 examples that eventually preserve energy. And that is, I can say that both R and T are real, but R14 equals minus R23. Meaning that what I have here is that if T and R are real, but here there's a minus sign, or here of course, then we're good. Then it works. Or, that's option energy preserving common choices. This is what we call the Fresnel choice, because this is what happens when you assume, this is normally what happens when you think about Fresnel reflection on the 2 sides of a partially reflecting mirror. If you have, usually if you have a transmission between index 1 and index 2, then the reflection here is n1 minus n2 divided by n1 plus n2, and the reflection here is of course the same, but opposite sign. So normally, from Fresnel reflections, Fresnel equations tell us that for the interface between two materials of different indices of refraction. There's another one which is the symmetric choice. And that is to assume that T, what did we have? T 3,1 equals T 2,4 equals T. This one is real. And R 4,1 equals R 2,3 equals I times R. This one is imaginary. But the reflection is imaginary. And if you check, then this also preserves energy. It's also close. What's the difference between those two beam splitters? It's just the question, when is destructive interference or constructive interference? In which phase? So you can choose any of those, and in reality you never know. So, okay. So now I want to say just a very little, I want to give, that's about it. I want to give some really short introduction to photon statistics, because we already discussed what a detector does. A detector output, what does it do? It tells me, it gives out what I think is I of t. It has a photocurrent at time t. But this is a result of an average over some integration time, tau detector, t detector, of what? The integral of from, I don't know, from t minus td to t, assuming it's a real detector, so it just looks on what happened on the time that we had before, and that was basically e of t minus tau absolute value squared d tau. So it gives me an integration. I can say that this is, I can define this as being some I average of t times what? Times td. Now, let's think, so that's always it. Now the question is, but I told you, so this is the photocurrent. Actually, that's not even the photocurrent. Let me be clear. During the integration time, we will see a number of electrons. Actually, I'm collecting charge. I'm collecting photoelectrons that are emitted and that are collected, and they reflect the response during that integration time. So this is not really I of t, this is the number of electrons of t. Now, so I can say, basically, and now let's assume that either the integration time is sufficiently short or that the intensity of the light is sufficiently low such that during the short integration time I may get an electron or not. So that the integration time is sufficiently short or that the intensity of the light is sufficiently low that during a single integration time maybe I get one. So then I'll ask myself, what's the probability to detect an electron? What's the probability to detect an electron? Now it depends. Now it becomes a question. So I can ask. Let me be more accurate. So I can say. So that is the clicking. The probability of a click between t and t plus dt. That's what I want to tell you. The probability to have a click. What is dt? That's the integration time of the detector. You see, the shortest integration time I can have. What is that? This is the intensity at time t. This is, I don't know, there is some proportionality factor times I of t times dt. Of course, the probability to have a click is maybe obviously related to how long do I wait and how strong is the intensity. So that's it. That's the classical relation. What's the probability to have a click in a really short time? Short enough time that maybe you'll have a click, maybe none. Then the answer is it's proportional to the intensity during that time times that short interval. This is the basic classical equation of photodetection. You assume that you have a photodetector that emits electrons, discrete electrons, and now we can say, okay, so given this, what is the probability to detect m electrons over a real time that is not infinitesimally small of, I don't know, over a second? So out of this, we would like to derive this PM photons between T and big T, and that is, so this is the probability of a single electron over infinitesimally short time. And this is probability of m electrons over t, not short time. We want to be able to derive this from this assumption. We want to derive this and to say something about its distribution. What are the possible m's for a given time? What do I expect? And so that's why, and this is statistics, and this will do שבוע הבא. As thank you all for listening, and I'll stop. If you have questions, I'll answer them.
אתה מגיע מחר?
מתי אני מגיע? זו שאלה טובה.
ואחרי השיעור אני אבוא אליך. מעניין.
אם יש שיעור השלמה, איך אתה תעשה אותו?
לא היית פה, אבל יכול להיות שהוא הספיק הכל היום.
גם את שיעור השלמה? נכון.
הוא אמר שאתה עכשיו מסיים גם את זה וגם כל מה שאבי היום דיבר.
ואת השיעור הבא שלו.
והוא יעשה פה סלטה.
כמה חומר אתה חושב?
אבל רק לאחור.
להכניס לראש עכשיו.
לפחות 2. אוקיי, הלו. wait. Okay. So, we're gonna talk about 3-level systems today. Completely different from 2-level systems that we talked last time. Also, before we start, after the class, check in the Moodle. There's a survey so we can determine what time we do the completion tutorial. for the tutorial that we missed last week. So check it. Yeah, okay. So free-level system has the same sort of background of two-level system where we have an atom, but instead of two-level, it has three. Crazy. But this distinction, this added level, allows us to do a lot of little game and explore different phenomena that we can't explore in a two-level system. For example, we have two types of phenomenon, which we will touch a little bit both of them today. First of all, is two-photon transition, which is the case where transition between two levels occur using a third level, mediated by a third level. Yeah, for example, a Raman transition, or let me just write a three-level system on the board and describe one of such cases it could be. Let's say we have 1, 2, and 3. If I want to make a transition between level 1 and level 2, and they're very close, so very close, E is very small, E is small, so omega needs to be small, so we have to do in radio frequency, and we can't really do that, this transition using lasers and stuff like that, if we're deep in the laser. So when we have a three-level system, we can just use the third level as help along the way. You can also see this two-photon transition type of effect in Raman spectroscopy, which we'll touch today later on. And okay, let me just write it. I'm gonna erase it in a second. First, two. Photon. And then 2, we have what we call driven coherence, which we will see today as well. Where we have, again, let's say that we have these two different transitions, 1 and 2, and they're not connected to one another, but their interference with one another can affect one another. So in a way, you can manipulate, do some, I'm purposely vague because we'll see an example today. We can do, we can manipulate interaction or state of ensemble of atom using two different transitions and the interaction between the two different transitions, which is a very cool thing that we can see sometime in quantum. Such effects, we know, I'll give you some names, electromagnetic induced transparency. Basically, when you have a material and you apply an electric field on it and then it becomes transparent and you can see through it, and when you stop the electric field, then it's become blocked.
Is it לראות אותו?
Yes.
נהיה שקוף.
Yes, yeah. There's a lot of materials like that. Diode kind of work like that. Don't tell Avi I said that, he will hit me. But it's true, I'm not lying. There's also effects called slow light, quantum memory, and also using three-level system we can do lasing without population inversion. Within the two-level system we saw that we have to have population on probably a laser course or something other that you took. We saw that you need a population inversion to make a lasing system, to get the net positive energy out of a resonator with an amplifier or something. In three-level system we don't need it, because it can do a lot of gains. All right. I'm gonna erase this. This was just named for now. So before we jump into different two different examples of uses of three-level systems, we need to acknowledge that while two-level system is just a ladder, three-level system, the two-level system has only one configuration. Three-level system is crazy. It's 3 levels. We have 3 different configurations. Insane. So first of all, it's also another ladder. And go like this. Usually, we write the lower level as 1, the higher level as 2, and a transitional level It can be in the middle, it can be above them, and in transition level we usually write as 3. Just so you, because you might come up in this tutorial later, but yeah, 1 and 2 are either the lower and higher of the beginning and end, or usually 1 is the starting position and 2 is the ending position of the overall transition. So we have a ladder system in free level system. We have a V transition, which is let's start here, go down to 3, and then go up to another level. Let's call it 2. Right. This is a V transition. V, a ladder. And then there was, I like to call it the A transition. 1, 3, and then 2. Although usually in literature you will see it written like so, but I think it's much easier to remember it as an A. This is all you can check with. There's no really other way to write a free level system, and each of them has some specific uses. We can also define some values on them. For example, let's take the V position. We can also define a line here. I'm going to erase this line, called delta, which is the decoherence between level 3 and the transition to our initial and final states. Of course, we can have delta 1, 3 and delta 2, 3, but in general, usually just a couple of delta. And then there's sometimes we also write a lambda, which is the general decoherence of the entire process. Yeah, but all of that's boring stuff. Let's start with some fun. All right. Fun examples. All right. We'll start with one of my favorite examples in this course, actually. Part state. Let us assume that we have I wonder if, let's say an A system, yeah. An A system, for example. 1, 2, and then some transition on top. And we have a process that can do two different processes that can transition from 1 to 3 and from 3 to 2, but we have no direct talk between 1 and 2. Okay? Also, for simplicity, I will assume that there's no decoherence with the third level, and also no decoherence between the entire process. All the lasers are perfectly tuned. Okay, so now I want to argue. I'm going to give you the final result, and then we'll get it. To look at the process, I want to argue that in this state there is a stable eigenstate that's equal to omega 2 1 minus omega 1 2 divided by square root of omega 1 squared plus omega 2 squared. Again, omega 1 omega 2 is just the Rabi frequency of this transition, especially. I want to argue that this state exists. Well, we only have population in 1 and 2. It's an eigenstate, which means that is I don't need to explain it, but what's most interesting about it is that it's an eigenstate that is completely decoupled from the Hamiltonian, which we'll see what it means and what the implication of it means for us. The last thing I want to argue about it, it's not really physics argument. You'll see that it's very fun, this state, and we can do some crazy stuff. Okay, so how do we approach this kind of question and try to find it? Well, we write the Hamiltonian. We are physicists, we have only like 2, 3, 4, maybe 5 tools in our belt. So 1 divided by h bar 2. Go 1. G1 E plus E G1. This is describing this transition. Now for the other transition, 2 G2 E plus E G2. Right? Now we want to find the eigenstate and eigenvalues. Well, we can write this entire matrix, entire Hamiltonian as a matrix, divided by 2. First line, third column, so it's 0, 0, omega 1. Second line, third column, 0, 0, omega 2. Then, of course, it has to be remission correct. This is our Hamiltonian. Of course, to find the eigenvalue, what I need to do is find the actual value of this determinant of this. 1 divided by 2 minus lambda 0 h bar omega 2 divided by 2 h bar omega 1 divided by 2 h bar omega 2 divided by 2 is lambda. Okay, I'm going to do it. I'm going to try to do it as quick as I can because you probably did it a million times. It's lambda whole squared minus h bar omega 2 divided by 2 squared plus lambda h bar over 1 divided by 2 squared equal to 0. Okay. Well, first result that we have right here, lambda equal to 0. And then the second one, I'm just going to give you the solution for the second and third result. Will be equal to plus minus h bar divided by 2 square root of the 1 squared plus omega 2 squared. Right. Now, technically, the question wants us to find all the eigenstate, but I'm going to ignore these two. I don't care. I'm just going to look at lambda equals 0. So we'll call it lambda dark equals 0. Means that 0, 0, omega 1, 0, 0, omega 2, omega 1, omega 2, 0 times A, B, C is equal to 0. So it's very easy to see. Second warning. It's very easy to see that C2 must be equal to 0 and A omega 1 it's equal to minus B omega 2. And if you take A equal to omega 2 and B equal to omega 1, or B equal to minus omega 1, and normalize it, you'll see that the state that we described, dot state here, equal to 1 over square root of omega 1 plus omega 2, squared, omega 1 minus omega 2 minus omega 1, 0, which is this. Amazing. Almost like I planned it all along. Okay, but what does it mean? What does any of this mean? Of course. Here? This one is a complex conjugate of this one.
המקדם של... טוב, אני הולך...
Oh,
Okay.
okay. This is something that I kind of skipped over, but not disturbing generality. I forgot how exactly you say that. You can take the Rabi frequency to be real.
אוקיי.
Usually, there's a lot of cases like that, but you'll see. But here specifically, whenever we talk about Rabi frequency, we can take them to be real. It's fine. If not, we can just rotate our system a little bit. Fine. Where was I? Oh, yes, right. So this is this is the eigenstate of the dark state. This one I won't do. You can find it in your notebook. It's not important what I'm going to talk about. We're not going to acknowledge it today. Alright, so since we see that the eigenvalue is 0, means that if we activate our dark state on our Hamiltonian, we'll get 0, actual 0, not the vacuum state, not nothing, actual 0. This means that this state is completely decoupled from Hamiltonian, and it won't change at all over time. So we have two lasers shooting at the system, and we have this dark state. It will stay constant always. Yeah. If we start there, we'll see. Now, you remember this was a long time ago, 2 weeks. You remember in two-level system in the Bloch sphere we talk about a diabatic passage. I did this kind of stuff. I can do it again because as I said this like 5 minutes ago, physicists only have like 5 tools in their belts, and we know how to use them in a million different ways. So let's see that I can use this dark state. I'm just going to do it conceptually. It's not going to be all about. I'm going to use this dark state to take all of my atoms or all of my electrons, whatever, from the ground state 1 and move them to ground state 2. And because we're staying in the dark state all the time, we're not using the transition state. But there is no connection between 1 and 2. So how I'm going to do this, let me just, I'm going to put the erase. I'm just going to erase some stuff that we already used. Alright, that's me. Right, so we start from all of our electrons, all of our atom G1, and we define it as some dark state. How can we do that? We basically don't put any laser on one. That's it. Very simple. And now I'm gonna shine our system with 2 different lasers, omega 1 and omega 2. The temporal cross section, temporal figure will look like so, right?
How is the light intensity?
Yes. Right? So I'm going to start with increasing the second transition, which again will do nothing because there's no atom in this state here. And then I'm going to increase very slowly, much slower than the transitional time of all the processes in the atom, the laser that affect the first transition. And like so, I'm going to stay, it's kind of hard to say conceptually, but I'm going to stay all the time in this dark state, but I'm going to slightly change the balance between the 2 arms. And because I'm in the dark state, the Hamiltonian supposedly doesn't do anything and stays in the dark state, this state, which is slowly changing over time. So there's some you can sort of prove all the time length that's necessary to do it, but we're not going to do it. This is just conceptual, fun stuff. But the bottom line is, I did magic. Transform from 1 to 2 without going to 3, even though there's no row from 1 to 2. Classically, it's impossible. Quantum says, I don't care. I'm going to do it anyway. Yeah. So this is one useful thing you can do with the three-level system, and make a transition without going through a third step. I don't know what's the physical uses of it in the world other than it being cool, but I like it.
Is there actually no use of the third level, or do the atoms like bounce and immediately decay to 2?
All right. In this specific example, we don't enter the third level ever.
Well, actually.
Row 3, the population density of 3 is 0. All the time. All the process.
A use for it is if you have a hybrid system where, say, levels 1 and 2 are each their own qubit, or say something like that, and they have long coherence times. But level 3 is a qubit that has really short coherence time. So you want to connect 1 and 2 to each other, but they're not very good at connecting. So you use 3, which is good in connecting, as a passage between them, and you don't want the information to be in 3, so you use this kind of passage. So the information is never at 3 because it has like short coherence time, and it passes from 1 to 2.
That makes sense. that makes a lot of sense there. Good.
אז בעצם אנחנו עושים מעבר דיאבטי, נכון? ממצב 1 למצב 2, אנחנו מדליקים את לייזר 1, ואז אנחנו עולים, ואז מתחילים להדליק את לייזר 2.
We turn on the laser on the empty side of the system, and then slowly change the balance.
ואז הוא עובר בצורה דיאבטית.
Yeah, and then we pass through we pass it diabetically with remembering that this dark state is completely invisible to our Hamiltonian, so we won't crash out of it or something, move out of it. We'll stay here, really stay here, while we transition all the electrons without moving to point 3. And as an example, I didn't quite catch your name.
Dotan.
The example that Dotan gave, where the level 3 is very useful for transition, but it's very lossy, for example. So very lossy, very noisy. You lose you get some decoherence over there or whatever. So it's mostly fun because we see quantum stuff that can't be happen classical. Okay. Well, this was the easy conceptual fun part. Now it's time for the hell mathematical part of this tutorial. Good luck. We're going to talk a little bit about Raman scattering and 2-photon transitions. Note that in the beginning of the class I gave 2 useful categories for three-level system and the uses. This was the second one that I said. This was driven coherence. Now we're doing 2-photon transition, which is the first example that I gave in the beginning. Yes. Okay. Okay. So as I said before, 2-photon transition allows us to overcome a lot of restriction that 2-level system give us. For example, if you want to transition between hyper fine states that are too close together to drive them with lasers. And there are more examples in the tutorial notebook gonna at least study one of them. One of this example we can see using a Raman transition, where we can have two non-coherent layers, levels, non-attached level, have some coherence between them. You'll see all of it as we talk and get into the math. So let's again start with a system. Sorry, it's a 2. Right. But this time we do have some decoherence line, which is this distance. I'll call it delta. The distance between those two, I'll call it lambda. And the one goes to delta, 2 goes to delta plus lambda.
Could you please explain the decoherence effect on the energy level?
It doesn't affect the energy level. The energy level is a property of the atom. Decoherence basically means that they come, if we talk simply, I come with the wrong frequency of the laser, so we'll add a phase, inefficiency, and transition, and all the effect that you saw in two-level system, or when we talk about the Bloch sphere representation, you'll see here. Just here is a little bit more complicated because we have another nonsense here. Right, and of course, like both of them, in this case specifically, both of them have two different level of decoherence from the third level. Okay. Second. Yes. Okay. Delta will be equal to 1 and 2 minus omega 1. The omega to 1 equals to E2 minus E1 divided by H bar. And then I need other details that I need to give. No, I think that's oh, actually, I wrote it the wrong way around. Level 2 is the one that goes to the delta. So delta equals omega L2 omega 2 3 minus omega L2. Right. I think that's all of the details that you need to know. Okay, sure. So first of all, we got the Hamiltonian of the system. H equals HA plus HLA. Well, HA is the non-interactive term, so we write it here. HA equal E1 1 1 plus E2 2 2 plus E3 3 3. HAL's interaction term equal minus H bar over 1 divided by 2 E to minus I omega L1 T 1 plus E to the I omega L1 T 1 3. Okay, there's nothing crazy here. Plus, actually minus H bar omega 2 divided by 2. And then very similar to the first term, e to the minus I omega L2 T 3 2 plus e to the I omega L2 T 2 3. Okay, it's very simple. Usually, we will try to transition to the rotating frame approximation here, but we have two different frequency with two different decoherence, so it's not very simple, but we can still do it. I'm gonna define some arbitrary unitary transformation equal to over j equals to 1, 3, e to the minus I lambda j t j j. Can you see why this is? What is it? Wait, what is it? Is it unitary? Because it's unitary. Do you believe me? You don't just believe me. Do you understand why?
I think I believe you.
Just multiply this with this complex conjugate. This time itself will just be itself, and this time its complex conjugate will be 1. So you will just get an I matrix. That's it. Okay. Now I will argue that the transformation of each part of H would be u dagger H u plus some time correction du dagger t u. This is technically another form of unitary transformation that you can do to an Hamiltonian. It's legal. Trust me. Okay. So now let's do. There's also like the E. Well, right. This as well because it's important. U. Crazy. All right. Back to the important stuff. The Hamiltonian. Let's calculate this.
You done.
Huh?
What you done?
Am I wrong? I'm never wrong. I'm wrong. Okay. Yeah, it's supposed to be like. Anyways, let's do the transformation. So let's start with the first part, the simple part. U dagger H U equals to U dagger H A U plus U dagger H A L U, right? Now U dagger H A U, since H A is only the diagonal part of the matrix, and the U transformation matrix is only the diagonal part, you can just take the exponent out, and this one just be equal to HA. Alright. Now the second part. I'm just gonna remove this plus, do a little box here. I'm just gonna erase it. Just do the second part. Okay. Now this one will be equal to, I'm just gonna laze through it. When I put it on the left, 3 stays 3, and put it on the right, 1 stays 1. Only terms that gets added are the term with the exponent. So I'm just gonna write it really quick. Not do it in steps. Number 1 divided by 2. E to the minus I omega 1 I minus lambda 1 plus lambda 3 t 3 1 plus E I omega L1 minus lambda 1 plus lambda 3 t plus, I'm just gonna call it HL2 wave, just so I don't, sorry, spell it. If you want me to write it explicitly, so you can write it explicitly, I'll write it. You want, but you want, it's also in the notebooks. No. Yeah, just writing the exact same equation again, just replacing the 1 with the 2. It's the exact same thing. Alright, okay, so let me. Okay, just let me drop it. It's important part of the proof.
אם אתה עושה U conjugate, זה נגמור את הסדר של הברקט, נכון?
Yeah, but
הסכימה הזאת, כן.
JJ is JJ.
לא, יש מניע פחתן.
You just do conjugate on the U. So the only thing that will change is the minus sign here, which is why we have a minus and a plus. Plus for me.
אני פלאים כבר.
Don't we all? Okay. Now let's define. Since I took arbitrary lambdas, I can define them as whatever I want. So let's define lambda 1 minus lambda 3 equal to omega L1, and lambda 2 minus lambda 3 equal to omega L2. I didn't do anything illegal, I just made some definition, and bam! I lost the exponents. Lost the time-dependent term, which is what's annoying with a lot of Hamiltonian, but we're not done yet. Not done yet, we still have one term to calculate. I, h bar, do u dagger t, u. Right? This will be equal to I h bar, sum for j, I lambda j, e I lambda j t, j, j, time, sum over j, cos j for 1 equal to 3. E to the minus I lambda j t, j, j. Right. Now, this one will give us a delta function, these two here. So we'll have minus h bar, sum for j for 1 to 3, delta j, j. Just a little bit of a transition to a Hamiltonian. Alright, now, if we'll just look for a second at HA and and this term together, we'll get that. So we got, let's call it A plus, I don't know, equal of j equal 1 to 3 of ej minus h bar lambda j, j, j. Again, this is just this term plus ha. From no, not plus here. From this, I can arbitrarily take lambda 2 equal e2 divided by h bar, and therefore lambda 3. I take it to remove the h2 term, to remove the 2 term. Lambda 3 will be equal to e2 divided by h bar minus omega L2. Lambda 1 will be equal to omega L1 minus omega L2 plus e2 divided by h bar. Okay, so we got some terms. Okay, so overall we have this time Hamiltonian will be equal to this plus minus h bar omega 1 by 2 3 1 plus 1 3 minus h bar, we get 2 divided by 2 3 2 minus 2 3. Well, I want to close the box. It's a beautiful box and you won't laugh at it. Alright. Everything is as it should be. Alright, okay. We're almost done. Almost done with defining the Hamiltonian. Almost done. So far, I didn't actually do a lot. If you're a keen observer. And the crux of this question will come soon. What's the time?
640.
6:40? Alright, we'll do a little more and then we'll take a break. I like how you think. Anyways, so let's look at these terms. Let's see if we can simplify them a little bit. So the first term, j equals 1, equal to e1 minus lambda 1 minus h bar lambda 1, which equal to h bar omega L2 minus omega L1 minus omega 2 1, which is just here this lambda that I defined, the coherence term. The second term defined earlier to be 0, 0. And the third term, h3 minus h bar lambda 3. You can believe me, will equal to minus h bar delta. This delta, which rusts with rust. Thank you. Okay, so now we finally done. Almost finally done. We just need to write it all down. I'm gonna write it here at the bottom. Then we'll keep it with us for the entire question. H bar. Oops again. Delta. Yep. Yeah, not so much.
חוצה פשוט המטריצה.
You're right.
כן, מה אתה עכשיו רושמת?
I think it will, because this is how it's in my notebook. But your solution is much prettier. Thank you. Okay, so the matrix will be 1, 1 is h. Let's take an h bar. H bar. H bar the outside. So 1, 1 is delta, lambda, and 1, 3 is minus omega 1 divided by 2. 1, 2 is 0, so it's this one. This one is minus omega 1 divided by 2. And then 2, 2 is also 0. 2, 3 is minus omega 2 divided by 2, so it's this one. And 3, 3 is big old triangle. So what's that?
ההפרש בין כאילו בין הלייזר, לא?
Delta,
או שזה הפרש בין הלייזר הראשון.
the small lambda is the difference between those two decoherents, and the big one is the difference between 2 and 3.
אז small delta זה בין הראשון, זה דלתה.
Okay.
רוצה להתערב לזה?
No, I believe you. I always forget the Greek letters. It's a thing. Everything is that all three or something. I don't know. Yeah, but
אז הלמד.
yes, the cool lamed. Yes.
כן, אז יהיה הפרש בין
It's the two photon detuning. It's the difference between
ההבדל ביניהם.
the mismatch here that they two have, and this is called the auxiliary detuning if you care. The auxiliary detuning, and this one is called the two photon detuning. Auxiliary detuning is like the offset, and the delta is the right. So do you want a break now or like half an hour?
שעה וחצי, למה הולך הפסקה?
Alright, so the no break.
רוצה הפסקה?
No, too late. Give your chance. Okay, this was part A of the question. Just organizing the Hamiltonian. I'll erase everything except the Hamiltonian. Part B. And I'll remind us, I don't know if you caught it in the beginning, we're trying to find some coherence between 1 and 2. So to show that they directly affect each other somehow. So in part 2 of this question, they say, okay, move from Hamiltonian state, go to איזו צפיפות? ברח לי המילה. Density matrix, thank you. I don't know what happened. Go to density matrix. In addition to that, assume that there's some sort of loss, some sort of decay on 3, 1 and 2. And we have gamma 3, 1 and gamma 3, 2 in our system. And they tell us that the dynamic of our density matrix equal to 1 divided by IH bar rho plus L relax of rho, where L relax equals to minus gamma 3, 1 divided by 2, 3 rho plus rho. This is not Lagrangian. This is a different L. It's its own very unique L. 1, 3. Sometimes when you add correction to this equation that depends.
The term is 3, 3, not 3, 2.
3, 3. 3, 3. 3, 3. Then this weird term. Soon we get to the 2. Anyway, but I was saying, yes, this is usually how you write the correction to the evolution of in time of the density matrix when you have some sort of decay, loss, whatever. Minus rho 3, 2 divided. I need a bigger board. Can somebody please tell the I don't know, Yossi or something? I need a bigger board. That's a great idea. Minus 2 to 3 rho 3 2. Right, and they want us to show to find rho dot. They want us to find rho dot. I'm not going to find the entire rho dot. I'm going to show one term, and you can do if you want the other terms. Although the solutions are again in the notes.
The symmetry part of it bothers me. The 3, 3, both of them, because it's like L dagger L and L dagger, or they're both the same. You know what I'm saying?
L. What?
Do you know how you get the 3, 3? Because like in the Lindblad-Messer equation, which this is, the Lindbladian term looks like L dagger L, where L is your decode. It's the gamma 1 3 1 or gamma 3 2. So the 3 1 and 3 2 is basically the matrix 3 2, like that. So that would be the L, right?
I show you coupling like so, because the decoherence to 1 shouldn't. I mean, I think it's logical that the decoherence to 1 wouldn't be dependent on 2.
No, yes. I just mean that it would be 3 1, right? But wouldn't you get 3 3, and then the other one would be 1 1? Because it's not symmetric. And I think you might be right. It might be like L dagger L.
This is not really my field, so I can't like confirm it.
Okay.
Like that this is correct physics. This is what the question gave.
Okay.
This is the. I mean,
You're
we can talk about it. I mean, it's an interesting conversation, but we should probably keep it after class.
Okay. Sorry.
If you want to, I'll also be happy to hear about it, but I don't have an answer.
No, I'm just not sure because I never do this in like this sort of.
Me neither. I do a lot of quantum optics, nonlinear optics and stuff. That's not.
Yes, that's not bad.
Okay. Where was? Oh yes. You want to find rho dot? I'm just gonna do one. right? So how do we find the row dots? Specific one. Well, we take this row dots of ij would be equal divided by 1 divided. We're missing brackets? I think there should be brackets here, maybe. Right? Here?
Oh,
Because it's not in the text and I think it's wrong.
no, there aren't supposed to be brackets.
So there's a mistake in a different part of the text. Good. Alright, anyway. Yeah. Yes. Especially row J. Basically take
Oh,
that's the expectations of it. It's nothing special. We did it before. Plus I-L relax. J. Okay. Yes, this is gonna be long. So if any point you want to skip, let me know.
skip.
What?
Skip.
There's only so much I can skip. You gotta let me write something first.
Just skip it.
Okay, so the final. I almost said the final solution. Anyways, let's do row 2, 3, and let's do this term. Actually, let's do the cooler term, the second term. This term. Right. So 2 row H 3 will be equal to 2 row times H bar delta lambda whatever 1 and it's H bar delta 3 minus H bar omega 1 divided by 2 3 1 plus 1 3 minus H bar. Need a bigger ball. 3 2 plus 2 3 Right? Now we can erase terms from the right, which means I'm just gonna multiply this 3 with everything here and see what I can knock down. 3 is 1, nothing. It's a better one. Nothing. Huh? 3 is 1, nothing. 3 times 2, nothing. We'll get minus H bar delta 2 row 3 minus H bar omega 1 divided by 2 row 1 minus H bar omega 2 divided by 2 row 2, which of course I'm going to replace all of these terms in terms like this: row 2 3 indicated second third, row 2 1, row 2 2. Simplicity. Yeah, I'm not going to write it again because we don't have time. Okay, that was okay. eventually, at the end, we'll get for row 2, 3, row 2, 3 dot will be equal to this is after everything minus I delta plus I row gamma 3 divided by 2. Gamma 3 is just gamma 3 1 plus gamma 3 2. Row 2 3 plus I omega 2 divided by 2 row 3 3 minus row 2 2 minus I omega 1 divided by 2 row 2 1. Bit weird. Okay. So the same process to find the time evolution of our density state, of course not completely because we still have those 9 terms. You can do this step for every single term of the 9-term matrix. It should be very fun and totally not long and agonizing. And luckily for you, you don't have to. Right. Anyway, next we want to solve a very specific dynamic. To try to simplify this equation, we assume that delta, this occurrence right here, is much bigger than all the omegas, all the gammas, and the small delta. Right? Which means that the relaxation to steady state of the state 1, 3, and 2 and 3 will be much rapidly, it varies much more rapidly than those two interactions. Maybe I should write the. Do you have the notes in front of you?
Yeah.
Would be. Right. So go up a little bit. I don't want to write like 7 equations on the board and waste our time. So just go up a little bit to here. Yes, this one. You see how you can also look if you want. Row 1, 2 dot has no term with the delta. It's much slower than the other terms, these two terms. And let's see what else does it say. Now we want to show row 3, 3. Between the population of 3 and the covariance of 3 between 1 and 2. So I want to look at this of the mean and the connections. So there it is. Okay, I can erase the button now, I don't need it anymore. So if you look at the books, we see that row 3 dot be equal to minus row 3 plus I omega 1 divided by 2 row 1 3 minus row 3 1 plus I omega 2 divided by 2 row 2 3 minus row 3 2